Hi everyone, Eric Bridenbaugh here. Today I wanted to talk about the subject of zooming with your confocal microscope. So in my travels around providing training and support for people, I've often found that the ability of a laser scanning confocal microscope, such as the FE3000 here in the UT Dallas core facility, people are often scared to zoom in. I think there's a fear of thinking zoom is just digital zoom like you might do on your smartphone. So I wanted to talk a little bit about that and how to consider, when to zoom, when to not, and how that will impact your data and why it's probably one of the most important features of a laser scanning confocal microscope. So that being said, first thing that's important to kind of recap on is that a laser scanning microscope acquires the image 1 pixel at a time. It does so by rastering a laser left to right, top to bottom across an imaging field. And as the laser goes across the image, it's going to encounter fluorophores in your sample, and that would cause a spike in fluorescence intensity. With each one of those spikes, you can then digitize the sample, so chop every little line of the laser trace up into little individual bits that become the pixels of the image. And then those pixels are assembled into a grid pattern that then makes up what your final 2D image is on the screen. So for instance, this cell picture we have here. So when talking about image generation, again, it's important to note that it's occurring 1 pixel at a time anytime you're working with a laser scanning confocal microscope or a laser scanning multiphoton microscope. Because it's 1 pixel at a time, the user has a great amount of flexibility in that they can decide exactly the number of pixels they want to use, as well as how big each individual pixel is. Now, this is where the choice comes in of how we want to shape our pixels in the image. So more pixels, our HD cameras and HD monitors we have these days, more pixels are great, looks great, etc. But because we acquire the image 1 pixel at a time, more pixels means longer acquisitions time. Now, smaller pixels, which often comes with having more pixels, also means that there's more laser irradiance. You're having to expose the sample to more laser zaps as the laser moves across the sample, which could therefore increase photo damage in your sample. Now, the way that we go about adjusting the size of our pixel and the number of the pixels in the image is through both zoom ratio adjustment as well as scan size adjustment. So right here I have the software for the FE3000 displayed, very similar on the FE MPRS multiphoton microscope. And if you work on any other confocal, older models, different brand, etc., somewhere there's likely very similar functions. And so the two most important values to consider are, number one, your zoom ratio, which is pictured down here at the bottom. Now, the zoom ratio changes the field of view of your image while maintaining the same number of pixels. It effectively squeezes your pixels into a smaller space, and therefore higher zoom will create smaller pixels. Along the same lines, we also have the scan size adjustment. Most confocal microscopes, you're able to change the number of pixels in the image, 512 by 512 pixels, 1024 by 1024 pixels, or as displayed here, 256 by 256 pixels. So if you have the same field of view, but you add more pixels into the field of view by increasing your scan size, you're naturally also forcing every pixel to become smaller at the same time. Now, I think, as I noted earlier, that the source of people's hesitation to grab that zoom bar is the notion of, okay, are we doing true optical zoom here, or are we doing a digital zoom? Again, everyone has a smartphone that you could pinch and squeeze on the image and you zoom in for digital zoom. So let's discuss the differences between optical zoom and digital zoom as it relates to a confocal microscope. So here I've got a little tiny image on the screen. Again, this would be my original image. So what's the impact of digitally zooming the image versus optically zooming the image? So with a digital zoom, we look at over here, what we've effectively done is just taken this little picture and blown it up, just stretched it. And we're relying upon computer interpolation to stretch these pixels out and try and guess what this blown up image should look like. Okay. Now, conversely, over here is an optically zoomed image with the confocal microscope. Here we've actually added more pixels into the image so that we have more detail in the image as we're zooming in. Okay, so over here, we've only sampled the image the same as our original, and we relied upon the computer to guess what this new larger image should look like. Over here, we've actually put many more smaller pixels into the image, sampled more frequently, in order to get this optically zoomed image. So with digital zoom, as I mentioned, we are enlarging the object in the image artificially by increasing the number of pixels, and most softwares will use a computer interpolation between pixels to try and guess what the new image should look like as you stretch it. Okay, there's no increase in resolution. You don't get any new information about your sample. You just make it bigger. That's it. So this becomes not an ideal strategy for scientific imaging, where data is of course paramount. Now conversely, optical zoom, you are enlarging the object in the image by sampling the image with a higher spatial frequency. In other words, you're grabbing more pixels per unit area to get more information about what it is actually in that image. So you get more spatial data, which is going to give you a qualitative and quantitative improvement in the actual image quality. By having more pixels in the image, you're able to discern smaller objects and identify smaller objects, as well as get more precise spatial measurements. The distance between 2 points in an image can be measured with greater precision in this manner. So from a qualitative perspective, optical zoom is pretty obvious. So again, here's another example to look at. Here is a 1x zoom image, okay? And so in terms of optical zoom, what I'm effectively doing here, I'm going to a 2x zoom. So I basically zoomed in, to make every pixel half as large, and then I've added more pixels to the field at the same time, so we can continue to see the same field of view here. And so with 2x zoom, you can see that some of these little lines that you see in the image, these little artifacts, are getting much more smoothed out. We're getting more detail in the image. And this becomes realized even further at my 4x zoom comparison, where now some of the finer filaments over in the 1x zoom, which kind of blur into one big fiber, we're now seeing two distinct fibers when we have basically shoved in 4 times as many pixels into the field of view. So what we are effectively doing here, as I've noted, is increasing our spatial sampling frequency. So we're going to do we're looking at the exact same 3 images previously, but now I've drawn a line across this. And so what I want to do is analyze the intensity of every pixel across this line to see what the quantitative improvement of higher sampling frequency, or smaller pixels, optical zoom, etc., is of the image. So if we look at these lines, which are the same exact place in all 3 images, and then we look at the intensities of every pixel along that line, as we go from 1x to 2x to 4x zoom, we see that we are really effectively seeing more detail in the image. So the spikes are broader here, they're more spread out at 1x zoom. If we jump over to the 4x zoom, we now see that we're seeing a much more finer detail for some of the dimmer filaments here. We're seeing more precise distances between the individual spikes that correspond to the actin filaments in the previous image. So again, this is all about higher spatial sampling frequency. If we sample more pixels per unit distance, we get more information about what's happening at every single point in the image. So then, we've discussed why zoom could be important, but then the next question is, what is the ideal pixel size? So I'm going to do a little demo basic example with some very simple shapes here to show the consequences of choosing too big or too small of a pixel. So in this case, we're looking at 2 objects, 2 circles on the screen here. And now I'm going to pick one giant pixel that's effectively larger than my 2 objects. Well, if I've got 2 objects in a single pixel, the resulting image just has one spot corresponding to that pixel. So we'd have no resolution. We're not seeing any separation between these 2 shapes. So 2 objects in sample, 1 object in image, no resolution. So we started off with a pixel larger than the sample. Well, what happens if we make the pixel the same size as the object? In this case, made smaller pixels. They're each about the same size as my 2 little circles here. But again, with it being the same size, we're still not able to separate them out. We do have a little bit more detail in the shape. It's now more rectangular, but again, we're trying to find two circles here. So again, two objects in sample, one object in image, no resolution. The real key is when you make your pixels half as large as the object in your sample. So in this case, I've made very small pixels. They're each about half the size of my circle. And now by sampling these, the resultant effect is that my image will display two separate and distinct spots with a gap between them. In other words, we now have resolution. We see two objects in our sample, and we also see two objects in the image as well. So I've been using the word resolution. Most simply, the best and easy definition for resolution in my mind is the ability to discern two objects in a sample as two objects in your resulting image. So we want to make sure that we have our pixels adjusted so that whatever we're trying to see, we can separate that in the image. So to resolve two objects in an image, you must sample the data with at least twice the spatial frequency as the smallest distance you want to see. This idea that your pixels are approximately half as big as your smallest object or smallest distance is commonly referred to as Nyquist sampling. So again, in other words, trying to make sure that our pixels are half as large as the smallest distance we want to resolve. There's a beautiful paper done by Jennifer Waters, a review of some of these common principles here. And I love this image. So right here we're looking at two sub-resolution fluorescent beads. These are smaller than any microscope could possibly see. And she's showing that if you use very small pixels, you're going to see two dots. But as your pixels get large, much like I kind of showed with my very basic shape example on the previous slides, as the pixels get larger, our ability to discern those two small dots as two individual objects becomes more and more difficult. By the time our pixels get much larger than the object, we now just see one kind of amorphous shape rather than two distinct circles as we should. So what is the smallest object we can see? What is the smallest pixel we want to use, and what is the smallest object we can see? The optical resolution of a microscope is the smallest distance between two objects in an image that can be resolved. Okay, it's determined by the point spread function of a diffraction limited spot created by the optical system. So that's the professional definition of optical resolution. Kind of more graphically depicted here. So the reality is a single point source of light never really looks like a point in an image. It actually creates what is known as a point spread function. And so you get this scattering of light as it passes through the optical path and eventually in the image plane. Now, this is looking at an epifluorescence microscope where you get this nice star-like appearance. This would be for a confocal microscope where we have this nice elliptical shape. And again, this is the axial point spread function in this picture. And if you look at it in the XY plane, it's more symmetrical, but similarly, a single point will be spread out over the distance. And so what happens then is if you have two dots, even no matter how small they are, if they're closer together than what the microscope can resolve, the appearance is just going to be kind of one larger shape rather than two separate shapes. So in order to actually resolve it, we have to spread out our point spread function, spread out this little distribution of light that we talked about until we have a gap between them that the microscope can then see. And then ultimately, we then have two distinct individual shapes. A great way to depict this is looking at an image of sub-resolution beads. So in this case, we're looking at 100 nanometer beads. Most microscopes can only see down to about 200 nanometers. So these are all smaller than what the microscope can resolve. And so if the beads are too close together, such as this shape here, or this shape here, okay, we're going to see what looks more like a rectangle or a peanut shape. But as the beads get spaced far enough apart, such as this spot here or over here, we can now see that that little spread of light that surrounds that little tiny dot is being pulled far enough away from its neighbor that we can see two distinct objects. So we would call this resolution. We would say this object is not resolved. These two objects are not resolved. So how do we calculate optical resolution? Well, if you do a quick Google search for optical resolution, you're going to see usually this formula right here. which is 0.6 lambda divided by the numerical aperture, NA. Okay, lambda is going to be the wavelength of the emitted fluorescence light, and again, NA is the numerical aperture of the objective, which you can see printed on the back or the side of just about any objective you look at. Now, if you look around, you'll see varying numbers for this 0.6. Maybe you'll see 0.63 or 0.6 or 0.7, etc. So it kind of depends upon how they're doing their math, but this is usually the average one. Now, this is lateral resolution, so we're looking in the XY plane with this value. If we're talking about confocal microscope, it's a single point of light for the illumination. So, and we also have a pinhole in the light path that cleans it up. So it's actually a little bit better. Our resolution for a confocal is about 0.4 lambda over NA. And again, if you Google around, you'll see anything from 0.33 up to 0.5 lambda over NA for confocal. But again, these are approximations. The Olympus software actually uses a more complicated method that takes in the specific pinhole size for every image, so as well as the excitation and emission light. So if you want to do some fun math to help you fall asleep at night, here's a good formula to calculate the exact resolution that any given confocal can generate. But fortunately, this is embedded in the Olympus software and does it automatically for you. Now, very important note, when you're talking about a confocal microscope, resolution is determined by numerical aperture and wavelength only. Magnification of the objective is not listed anywhere. Okay, so just because you're going from a 60x objective to a 100x objective doesn't necessarily mean you're increasing your resolution. It simply means you are shrinking your field size by going to higher mag. So numerical aperture is the most important value when selecting your objectives. Now, how do you acquire at the maximum limit? So how do you get the best possible image? So again, to acquire the highest possible resolution, your pixel size should be half of the maximum possible resolution. So in microscopy, we typically use the term Nyquist sampling frequency, and I've been using this word, make your pixels half as big. That's a slight approximation. In optical microscopy, the true value is actually the resolution divided by 2.3. The extra 0.3 is to account for some inherent imperfections in any optical system. If you ask an engineer what Nyquist is, they'll say you divide the frequency by 2, but in optics we usually divide by 2.3. And so fortunately, again, the Olympus FE3000 as well as our older confocal microscopes always calculate for you the optical resolution. So we're looking in the information tool window of the FE3000 software here. Our older models, the FE1000, FE1200, had a similar window. And we display for you the optical resolution. And so in this case, this is, I believe, a 60x oil lens. And so it's displaying for you that we could theoretically resolve 0.1749 microns per pixel with this particular objective. If we wanted to image at maximum resolution, i.e. image at Nyquist, we'd want to take this 0.1749 divided by 2.3 and then adjust our pixel size here. Here's our actual pixel size. Adjust our pixel size either by adding more pixels to the image, by changing the scan size, or by zooming in to make every pixel smaller. So by changing the scan size and zoom, we would want to adjust this pixel size to be our optical resolution divided by 2.3. Most people usually just divide by 2, keep the math easy in their head, but if you want to be a purist, you divide by 2.3. Now, if you read the microscopy literature, the thought leaders in microscopy believe firmly in Nyquist sampling frequency. So it's always said that Nyquist sampling frequency is ideal. That's what you should be using for the best possible microscopy images. And if you use less than Nyquist frequency, in other words, your pixels are bigger than Nyquist, that's called undersampling. And if they're smaller than Nyquist, that's called oversampling. Now, even though we stress Nyquist, most images out there are undersampled or oversampled. So, what are the consequences of undersampling? Well, if your pixels are too big, this creates an effect called aliasing. We already showed this with our little pixel size demonstration on the previous slides, but as an example, let's look at this square here. What is the shape we're looking at? Is this just a single black box? Well, if we sample this black box with greater frequency, we find that in fact it's not a black box. It's actually a series of alternating black and white spots. But if we zoom out too much, it'll look like just one black box. So this is called aliasing. This is an effect where sampling too infrequently may lead to a misinterpretation of the data. You might actually have two objects where your undersampled image is only showing one. Now, there are also consequences of oversampling. You don't necessarily just want to zoom into the max. If your pixels are too small, you could have increased photo damage because you're sampling the laser or blasting the laser on the sample more frequently than is necessary to get the best data. Additionally, if you're sampling more pixels with a laser scanning microscope, you're going to have a longer acquisition time. So more core fees, more time in a dark room, and more exposure of your sample to light. So acquiring your images with your pixel size adjusted to Nyquist ensures that you're getting the best possible data from your sample. You're getting the most spatial data and the most fluorescence intensity data. Okay, your pixels are smaller than your point spread function, therefore every fluorophore in your sample, in your image, is definitely captured by at least one pixel somewhere. So there's no possibility of you missing any data anywhere in your image. This will lead to the best possible image for quantitative fluorescence measurements, distance measurements, etc. So along the same line, if you want to use your image for measuring intensity or for measuring colocalization or for measuring distances, etc., Nyquist is always best because that's going to give you the most possible spatial and intensity data from which you can then measure. And I've only been talking about primarily XY pixel dimensions here, but don't forget about your Z-step size. Naturally, confocal microscope creates a three-dimensional image, and so there is a spread of light in the third dimension, the Z dimension. So make sure you adjust your Z-step size to satisfy Nyquist as well. So in other words, look at your optical resolution in the Z dimension, divide that number by 2.3, or 2 if you want to make it simple, and then make sure your step size is less than or equal to that value. Now, when can we ignore Nyquist? We can't. Nyquist is ideal, but there are some instances where it's not necessary. So when do we want to undersample an image? Well, we can use undersampling as a mechanism to get a larger field of view, and also to get increased acquisition speed. So as an example, if we look at this image here, in this case, this is an example of an investigator looking at cancer cells get attacked by immune cells here, and he needed a large field of view so that he could see numerous cells during the course of the time series. If he zoomed to Nyquist to acquire this image, the acquisition times would have been too long to keep the same number of cells in the field of view. So again, if you need to see a large field to have more cells, to have more objects to count, well then undersampling may be good for you. And if you need to keep your speed up, having fewer pixels in the field is beneficial as well. Now, another common reason is if you just want pretty pictures. In this case, we're looking at a single 1.25x magnification image of a mouse kidney slice. Naturally, this image is not captured at Nyquist. This was all about showing a big, giant piece of tissue. So again, if you need to have just a big, pretty picture, you're not necessarily zooming to Nyquist. You're just trying to make the picture look as visually appealing for your individual goals. Now, conversely, there are a few reasons to oversample as well. Sometimes you need to zoom beyond Nyquist. The two primary examples of that would be for deconvolution, which we have the licenses here in the UC Dallas core facility. It's a very powerful technique. It's a way to shrink the point spread function of the light in your image to a smaller spot so you can see greater contrast, greater detail. If you want deconvolution to work very well, you actually need to give more data to the image than Nyquist sometimes provides. So zooming in past Nyquist could be great for deconvolution. And it's also used routinely for any of the various techniques out there of super resolution. That is a way to achieve greater resolution than a microscope and objective can ordinarily attain. Now we've been talking about spatial data and making nice pictures, etc. But one common application where pixel size is absolutely critical is colocalization imaging. So in short, colocalization imaging is simply seeing whether or not two or more fluorescence signals overlap in a merged image due to those objects being close together. This is a very common request in many microscope applications involving fluorescence. So in working with colocalization, it's very important to keep your pixel size in mind. The reason is that the focal volume of a microscope, the single spot that a microscope can see, is often very large compared to a typical molecule. So over here we've got basically the point spread function of a common confocal image, about 200 nanometers in X and Y and about 800 nanometers in Z. So in that focal volume we can cram in a whole lot of fluorophores. So it's important to consider the spatial relationship. So again, colocalization in an image does not prove molecular interaction. It just means that these multiple fluorophores are co-occupying the same voxel or the same pixel. Okay, that is to say, if you want to ensure you can interpret this co-occupation, again, this is kind of my term to help explain colocalization. If you want to interpret co-occupation data, it's important that you image at Nyquist so that you know what your accurate focal volume is. If your pixels are adjusted to Nyquist, then a two-color fluorescence pixel, in other words, a single pixel in a fluorescence image, would indicate that two fluorophores are effectively roommates. They both co-occupy the same spot. They're roommates in a volume that is defined by the optical resolution of the microscope. So again, if we had a single yellow pixel on a green and red image, that would mean that a focal volume such as this 200 nanometers in XY and 800 nanometers in Z, if we saw two different colors in that spot, we could say those two colors are within that spatial relationship to one another. Now, everything I discussed thus far was all related to laser scanning microscopes. Again, because on a laser scanning microscope, you can pick your pixel size. But what about camera-based microscopes? Now, just because a camera-based microscope does not really have a zoom ratio that you can control, all the rules still apply. You still need to make sure that your pixels in your image are half as big as the smallest distance you want to resolve. Okay? But again, with a camera, you can't zoom. So all the pixel dimensions are fixed on a camera-based microscope. The trick then with a camera-based microscope is to select the magnification objective that yields pixels small enough to reach your imaging goals. So if you're working on an Olympus microscope with CellSense software installed, you can click on any image and there'll be a properties display. Okay, and so here's an example here. It shows you calibration X, calibration Y, and it's telling you the size of the pixel in the image. So again, make sure that your pixels in the image with your camera-based microscope are half as big as the smallest thing you want to see. Fortunately, most camera-based microscopes are set up by your microscopy representative such that the pixel size with particularly your high mag objectives are going to be approximately Nyquist or slightly larger than Nyquist. Okay, given that, as long as these pixels are half as big as the smallest thing you want to see, your microscope is probably adequate for the job of your imaging. Well, thank you very much for listening today, and hopefully this is helpful in building your confocal images going forward.
Thank you so much for that, Eric. With that, over and out.